Today, we unravel the mysteries of the seemingly simple operations GCD and LCM and how interesting they truly can be. So, most of you probably know the basics. Greatest common divisor is the largest integers that divide two or more numbers, and LCM is the least number that is a multiple of all the numbers of. So, for example, LCM mn is just the least common multiple of m and n. Let's take a simple example just to review before getting into some more interesting things. What is the ratio of the least common multiple of 180 and 594 to the greatest common factor of 180 and 594? First, prime factorizations. Let's do this. 180 is 36 times 5. 36 is 6 squared, which is 2 squared times 3 squared. So 2 squared times 3 squared times 5 for 180. 594, notice how it's 6 times 99. So 6 is 2 times 3. 99 is 9 times 11. So 3 times 9 is 27, which is 3 cubed. So 2 times 3 cubed times 11. Now, remember how GCD LCM, GCD can be found by taking the lowest power of the prime exponents from the prime factorizations of m and LCM can be found by taking the highest prime exponents from the prime factorizations of m and n. So the GCD of these two numbers, let's line them up. 2 squared times 3 squared times 5, 2 times 3 cubed times 11. GCD is the minimum exponent for each one. So GCD, what's the minimum of 1 and 2? For the 2, of course, 2 to the 1 is less than 2 to the 2. So 2 to the 1. 3 squared is less than 3 cubed. So times 3 squared and 5, and there's 5 here and 5 to the 0 here. And then there's 11 to the 1 here and 11 to the 0 here, right? Okay, so GCD is just 2 to the 1 times 2 to the 1 times 3, this should be cubed, sorry. 2 to the 1 times 3 squared times 5 to the 0, right? The minimum of 0 and 1 is 1 times 11 to the 0. And these are both 1, so we can just ignore them. GCD is just 2 times 3 squared. Now, LCM is the highest of each one, so 2 squared times 3 cubed times 5 to the 1 times 11 to the 1. So the ratio of the LCM to the GCD, we just take the LCM divided by the GCD to do that, and just divide like that. We get 2 to the 1 times 3 times 5 times 11, which is 6 times 55, 330. So that was a nice and simple example to get things started. We just had to apply the GCD and LCM properties and then divide. So here's another interesting property. The product of GCD and LCM is the same as the product of the numbers. For example, GCD of 24 and 36 times LCM of 24 and 36 is just 24 times 36. And why is this true? Well, notice how in the GCD, we take the minimum prime factor, right? So we would take, okay, from 2 squared and 2 cubed, 2 squared. And from 3 and 3 squared, it's 3. And for LCM, we take the biggest one. So we've got 2 cubed, 3 squared. And then when we multiply them together, we have one copy of the biggest one and one copy of the smaller one for each prime. And the same thing happens when we multiply the numbers. We have one copy of the big one and one of the small one, one of the big one of the small one for each prime factor. That's why they're equal. Okay, and you can find these examples in the Mastering AMC 8 book, free Mastering AMC 8 book with many problems and examples that supplements this video. You can find it in the description. Let A be the smallest perfect cube that's divisible by 15, 22, and 176. If A is B cubed, find B. So to do this, we're going to need to look at these properties here. The GCD of AC times and BC is just C times GCD AB. What does that mean? for example, GCD of 10 times, let's say 10 times 39 and 10 times 78 is just 10 times the GCD of the inside part, 39, 78, right? Same thing for LCM. LCM 10 times 39, 10 times 78, you guessed it, is just 10 times the LCM of 39 and 78. And another property, if a number is divisible by two numbers, A and B, it's also divisible by their LCM. Not necessarily product, LCM. For example, if we know that a number is divisible by 4 and 6, we don't necessarily know it's divisible by 24, because, for example, it could be 12, and that's not divisible by 24, the product. But we know it has to be divisible by their LCM, 4, 6, which is 12, which we know is true. Let's explore that in action. This one combining some principles from factors. Okay? Let A be the smallest perfect cubed that's divisible by 15, 22, and 176. 15 is 3 times 5. 22 is 2 times 11. And 176, well, notice how this is 160 plus 16, which is 16 times 10 plus 16 times 1, 16 times 11, or 2 to the 4 times 11, right? We just prime factorize everything. And we know that there's a perfect cube that's divisible by everything here. Remember what we just learned? If it's divisible by different numbers, then it's divisible by their LCM. So we know it has to be divisible by LCM of 15, 22, and 176, the number. So what is their LCM? To do this, again, we have to use our prime factor. We have to use our highest power logic. So we've got 2 to the 0 times 3 to the 1 times 5 to the 1 times 11 to the 0. That's 15, right? 22 is 2 to the 1, 3 to the 0, 5 to the 0, 11 to the 1. 176 is 2 to the 4, 3 to the 0, 5 to the 0, and 11 to the 1. So we take the highest power to find LCM. That's 2 to the 4, 3 to the 1, 5 to the 1, and 11 to the 1. So we know that the A be the smallest perfect cube that's divisible by these three things. This must divide A. So any multiple of this for our perfect cube is acceptable. But what about this perfect cube condition? How should we use that condition? Well, what do we know about a perfect cube? Let's say we have some number n and we cube it. Notice how, let's take an example. What is a perfect cube? We all know. 8. 8 is 2 cubed. So 2 cubed, right? Or so 2 cubed. Notice how the exponent in the prime factor is a multiple of 3. Let's take a look at something else. 6 cubed equals 216. This is going to be equal to 2 cubed times 3 cubed. Notice how all the exponents in the prime factorization are multiples of 3. And naturally that makes sense, because if you have anything cubed, whatever that number's prime factorization is, whatever it is, 2 to the a times 3 to the b times blah blah blah, if you cube it, it becomes 2 to the 3a times 3 to the 3b, so on, right? By exponent rules. So therefore, we know that a perfect cube has exponents that are all multiples of 3. So, multiples of 3. How do we do that? So, A is the smallest perfect cube divisible by everything here. It has to be multiple of 3 exponents. And let me just clarify here, the positive has to be positive. So for something to be divisible by all these things, okay, let's look at each prime factor. For a perfect cube to be divisible by 2 to the 4, what prime factor of 2 must it have? Well, it must be a multiple of 3, and it must be greater than or equal to 4 for it to be a multiple of this. And what's the smallest factor that's multiple of 3 and greater than or equal to 4? 2 to the power of 6. Now what about for the exponent prime 3? The smallest multiple of 3 greater than or equal to 1 is just 3. So 3 cubed. And we're, again, looking for ones that have multiple of 3 exponents and that are larger. Because you can't have something like 3 to the 0. It then won't be divisible by this expression. But it has to be already found that it has to be divisible by this. So something like 3 to the 0 won't work. It has to be at least 1 and a multiple of 3. And it could be something like 3 to the 6 as well. We're just not including that because we're looking for the smallest one. So 3 cubed times 5 cubed times 11 cubed. They're all going to be 3 exponents. So this is our perfect cube. Cool. And it says a equals b cubed, find b. So this is a. This is the smallest value of a, and it's equal to b cubed. B is 2 squared times 3 times 5 times 11. That is 12 times 55, which is 110 times 6, 660. And that's our answer. So again, just to summarize, the key idea for this problem was to look at the LCM condition, find all the prime factorizations, and then after that, what we had to do was notice that all the exponents must be multiples of 3. We got that, so b is equal to this quantity, 660. Cool. And Euclidean algorithm. So let me show you a quick example of the Euclidean algorithm over here. Okay? So let's say we want to find, make that a tad bit smaller, GCD, let's say, of 144 and 28. So rather than looking at these big numbers, there's a neat trick you can use. GCD of, so what you can do is take the larger number. Now subtract as many multiples of the other number as you can. So 144 minus 28 is 116. 116 minus 28 is 88. And we can keep going. 88 minus 28 is 60. 60 minus 28, 32. 32 minus 28, 4. Okay, now we got 4. So this is equivalent to GCD of 4 and 28. Now this was the slow way of doing it. You could have also directly seen 144 divided by 28. Oh, it leaves a remainder of 4. So what we do is we just take the remainder of this thing when divided by the other thing, and now it's just, and we have that by the Euclidean algorithm, these quantities are actually equal. And now we can do the same thing again. Take the larger one, look at the smaller one. So what is the remainder when the larger one is divided by the smaller one? That is 0. 28 is a multiple of 4. So this is equal to GCD, 4 and 0. And whenever we reach a point where one of the numbers is 0, we stop. Now, the GCD of 4 and 0, well, 0 is the multiple of everything, so this is just 4. So that's our answer. So the key idea is you just subtractively subtract the largest possible multiple of the other number until you get something like this, and then it's just this part, this number here. And you can find another example in the book. And now let's take a look at some harder examples. You can check out this example in the Mastering AMC book. It shows some cool ideas that are important. Well, let's take a look at this example from AMC's. How many positive integers n are there such that n is a multiple of 5, and the least common multiple of 5 factorial, and n equals 5 times the, okay, let's write this. The least common multiple of 5 factorial and n equals 5 times the GCD of 10 factorial and n. Okay, so to do this, we're going to have to find the prime factorizations. What is the prime factorization of 5 factorial? Now, one way is to expand that out and divide. But do you remember Legendre's theorem from our previous video? Well, we can find the number of prime factors of all the primes. So notice how 5 factorial is just 1 times 2 times 3 times 4 times 5, right? So it's not going to have any primes bigger than 5 because that's impossible if the maximum number we're even multiplying is 5. So now all we have to do is consider these 3 primes, 2, 3, and 5. Now we have to do is look for the exponent on each of these 3 primes. Okay, so what is the exponent on 2? How many factors of 2 in 5 factorial? We just use our logic. 5 divided by 2 is 2, remove the decimals. 2 divided by 2 is 1, 1 divided by 2, 0, and now we add them up, 3, so 3. Now what about 3? This is easier. 5 divided by 3, 1, 1 divided by 3, 0, so just 1. And for 5, it's just the same thing. 5 divided by 5, 1, 1 divided by 5, 0, so just 1. Whoops, looks like I'm in the way. Okay, so 1, 1. So 2 to the 3 times 3 to the 1 times 5 to the 1. That is 5 factorial. Now we can do something similar for 10 factorial. Okay, so 10 factorial. What are the primes less than 10 10? 2, 3, 5, and 7. So these are the only primes that are going to divide 10 factorial. We can't have something like 11 dividing 10 factorial. We're not multiplying anything that's a multiple of 11, so not possible. And to do this, we just use our same Legendre theorem. 10 divided by 2, 5. 5 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 0. So now we just add everything up to get 8. Now it's just a repetitive process. 10 divided by 3, 3. 3 divided by 3. And if you don't know Legendre's theorem, check out the previous video, Divisibility and Primes. 1 divided by 3, 0, 4. And now we just look at 5. 10 divided by 5, 2. 2 divided by 5, 0. Remember, we're dropping the decimals for everything. So sum is 2. And finally, 10 divided by 7, 1. 1 divided by 7, 0. So 2 to the 8 times 3 to the 4 times 5 squared times 7 to the 1. That is the prime factorization. Okay, that's good. So 10 factorial equals 2 to the 8 times 3 to the 4 times 5 squared times 7 to the 1. And now we can erase this so we can get some more room to work. And yeah, definitely check out the previous videos in number theory if you haven't already. Okay. So now what? Now we can write this as LCM 2 cubed times 3 to the 1 times 5 to the 1 equals 5 times GCD 2 to the 8, 3 to the 4, 5 squared, 7 to the 1. Oh, sorry, I forgot to include the n here, of course. You can't have a GCD of one number. So remember how GCD is the minimum of the exponents and LCM is the highest? Well, these things, what we can do is we can look at each prime factor separately. So first we look at 2. For 2, LCM of 2 cubed and n, well, must be equal to GCD of 2 to the 8 and n. What does that mean? That means the minimum, and you know what, let's do this to make it a little bit easier on ourselves. Move this a little bit here. And now let's say that n equals 2 to the a times 3 to the b times 5 to the c times 7 to the d. Right? Okay. 2 to the a times 3 to the b times 5 to the c times 7 to the d. And same thing over here. right? So the LCM of these two quantities will just be the highest exponent of each one. So for 2, the right side, it will be the maximum, the maximum of 3 in A. On the left side, it will just be the minimum of A and 8. So you're taking the maximum of A and 3, the smaller of A and 8, and those have to be equal. What does that mean? What if A is something like 1? Then, if A is something like 1, then the maximum of 3 and 1 is 3, and the minimum of 1 and 8 is just 1, and that's not equal. What if it's something like big like 10? Maximum of 3 and 10 is 10, minimum of 10 and 8 is 8, and those are again not equal. So essentially what must happen for the maximum of 3 and 8 to be equal to the minimum of A and 8 is that A is greater than or equal to 3 and less than or equal to 8. Because if A is any more than 8, if A is any bigger than 8, then the minimum of the two quantities will be 8, and the maximum will be A, and A and 8 will not be equal then. And if it's less than 3, the maximum of 3 and A is 3, and the minimum of 3 and 8 is if A is less than 3, the maximum will be 3, and the minimum will be A, which are not equal. But if A is in the sweet spot in between, then the maximum of 3 and A is A, the minimum of 8 and A is A as well. So they're equal. Just see it, maximum 5 and 3 is equal to minimum 5 and 8. They're both equal to 5, right? That's an example of the case that does indeed work. So how many such possibilities are there for A? Again, it can be anything from 3 to 8. So that's 3, 4, 5, 6, 7, 8. That's 6 possibilities. So 6 choices here. Now, what about for 3? So for 3, again, the maximum of 1 and B, right? LCM, maximum of B and 1 equal to the minimum of 4, 3 to the 4, and 3 to the B. So minimum B and 4. And like the previous thing over here, it's very similar logic. If B is too big, then they won't be equal. If B is too small, then they won't be equal. But if B is in between 1 and 4, then it does work. And just to show this, let's say we have something like 0. Max of 0 and 1 is just 0, is 1. It's not equal to minimum of 0 and 4, which is 0, right? And if it's too big, like more than 4, so 5, then the maximum of these two quantities will be 5, but the minimum of 4 and 5 will be 4, and these are again not equal. So it has to be in the sweet spot from 1 to 4. There are 4 choices. And now we're running out of room, so let's compress everything. Yay. Put that to the side. And now let's look at 5. Now 5 is the trickiest case. The LCM on the left-hand side will just be maximum of 1 and C. Maximum C and 1. On the right side, it's going to be 5 times the minimum of, so the prime factor will be the minimum of 5 of 2 and C. So minimum 2 and C, that will be the prime exponent, times 5, right? Because of this thing here, which is 5 to the 2C plus 1. So that means that max C and 1 must be equal to min 2 and C plus 1, right? Because it's just the GCD on this side will result in a prime factor of minimum 2 and C on the right side, and then plus 1. Okay, so when is this going to be true? Max of C and 1 equals min of 2 and C. So let's just take a few cases. If C is 0, then maximum C and 1 is 1, and minimum 2 and C, minimum 2 and C is just going to be 0. So this will be equal to 0 plus 1 equals 1. So when C equals 0, it works. Now, what about 1? Max C1 then will then be 1, and then minimum of 2 and 1, which is, or 2 and C is 1 in this case, plus 1 will just be equal to 2. And those are not equal, so that does not work. Okay, another case, 2, and it turns out that anything beyond that, 2 or more, it also will not work, because beyond that, anything bigger, let's try 2 just to see. Maximum 2, 1. For C equals 2 is 2. Maximum or minimum 2, 2 plus 1 is 3, so that doesn't work. Minimum 2, 2 plus 1 is 3. And now what about for 3? Maximum 3, 1 equals minimum 2, 3 plus 1. Max of 3 and 1 is 3. Min of 2 and 3 is 2. Plus 1 is 3. So, 3 does work. So C equals 3 also indeed does work. Okay, so now what? Now what about for 7? Look at here. LCM of this and this, it will just be D because there's no power of 7 on this term in the LCM. So for 7, just D. And on the right-hand side, for 7, it's going to be just minimum of 1 in D. So when is D equal to the minimum of 1 in D? When the minimum of 1 in D is D. So when D is 1 or 0. So D can just be equal to 1 or 0, right? So D is 1 or 0, as you can see here. So therefore, we get that D has 2 choices. Okay, so is that it then? Is there anything else we have to do? Well, let's read the problem carefully. How many positive integers or n's are there such that n is a multiple of 5? Aha. So therefore C cannot be 0. The exponent of 5 cannot be 0. Because it has to be a multiple of 5. So C equals 3 is the only case that works. So to summarize, 6 choices for 2, 4 choices for 3, 2 choices for, 1 choice for 5, right? Because C has to be more than 0, and 2 for 7. So that's 48. And that's our answer. Let's quickly recap here. Basically, we looked at this condition first. We found the prime factorizations. And then after that, we just had to do case by case. Look at A. Look at 3 exponents. We found that this must be true and it has to have 4 choices. We looked at 5 exponents and found this equation to be true. And then we saw 2 cases, C equals 0, C equals 3, but C equals 0 does not work, of course, because of the problem statement. And then after that, we just looked at 7, saw, okay, D has 2 choices, and then we're done. So the answer is just 6 times 4 times 1 times 2, 48. And that's all for this video, and we're going to check out modular arithmetic, the most powerful tool in number theory, in the next